So what we're going to do is we're going to solve this indeterminate problem here. What we have is we have a cap, a cylindrical cap, a cylinder, and inside of this larger cylinder we have 4 smaller cylinders on the inside. And each of these cylinders is made up of a different material. And what we want to do is we want to find out what happens when we apply F push, or force push, onto this cylinder system. And so what we're trying to find is the compression of the cylinder. So what we want is then we want to find delta of the system. But first, before we start, I'm going to make an assumption. I'm going to assume that the moment around the centroid of this, where the force is being applied, is 0. So that means we won't have the cylinder tipping over or anything. So we have the moment on the centroid equal to 0. So first what we want to do is we want to do the equilibrium equations. So what we do have is we have 0 is equal to force push minus these reaction forces right here. So we have minus R1 minus R2 minus R3 minus R4 and minus R of the case. And now that we have that, our second step is to find the force displacement. So what that is that'll deal with our delta. So we have delta 1 is equal to the flexibility 1 of that cylinder times the reaction at 1. So we have that, so we can keep going. So we got delta 2 is equal to flexibility 2, reaction 2, and we can do this for all of the cylinders in the system. So we have that. Now what we want to do is we want to solve for R, because we'll need that for later. So what we'll do is we'll take R1 is equal to delta 1 over flexibility 1. And we can do that for all of them, but I'm just going to do it for this one right now. And so then for step 3, what we want to do is we want the compatibility equations. So what this is seeing as we're applying a force on this cap, the entire system has to compress at the same for the same amount of distance. So what that means is we have delta is the same as delta 1, which is also equal to delta 2, and so on until we get all the way out to delta case. And we have that. And so now we can solve this problem. So what we'll do first is we'll take equation 1 that we have here, and we'll sub in for R this delta over thickness, or not thickness, delta over flexibility. So what we have is we have 0 is equal to force push minus delta 1 over flexibility 1 minus delta 2 over flexibility 2, and on until we get all of the cylinders in there. Okay, now we have that. And then what we want to do is we want to take into account this compatibility equation. So we can just change all these deltas to delta. So I'll just get rid of all the subscripts here. There's that. And now what we can do is we can pull out a delta from all those values. So we have force push minus delta times 1 over flexibility 1 minus 1 over flexibility 2 minus 1 over flexibility 3, and so on. Now we have this. So then we can add this to both sides. So then we'll just get force push is equal to this delta times the flexibility values. But what we'll do to save board space is we'll just divide force push by this sum, right, or by this set of numbers right here, to just solve for delta straight out. So we got delta is equal to 1 over f1 minus 1 over f2 minus 1 over f3 minus 1 over f4 minus 1 over f case. So that is all solved for delta. So we have our delta right there. So this is actually the answer to the problem. And so that is how we go through that system and solve that problem.